Welcome everybody to this talk, How Does the Internet Work? And our speaker is Peter Stugen. I'm very happy that he's here to explain to all of us how the infrastructure of the Internet really works. I'm pretty sure we will all learn a lot today. Please give a big and warm round of applause for Peter Stugen.
Thank you very much. Thank you for being here. This is amazing translation into French. Wow. So I want to talk about how the internet works and try to shine some light on all the technologies that are involved when we use the internet every day. So why this talk? Some motivation first, then a little bit of brief background, just how the internet got started. And then we get into the details. So what actually happens between the web browser and the website? That's the starting point. So in the description, I listed things from bottom up, so from the very low level packet stuff and through the various layers of the network stack up into the applications. And that's the building blocks part. But I inserted this overview first, what is actually going on between the browser and the website, because that's what most people already know and use a lot. Some parts, some details about the different protocols, and in the end, some recommendations for further talks if you find these topics interesting. So the reason I want to give this talk is to talk about how does the internet work, right? The mechanism that we use all the time, but aren't mentioned very much. So they are sort of obscured or well, I don't know if hidden is the right word, but we don't experience the network itself very much, right? We experience the various services that we use, and the services, they try their hardest to keep us interested, to tickle our imagination, and I think it's dangerous to not talk a little bit about the network every now and then, and to think about the network, and to actually fight for a public network that is available to all and equal, also neutral. If we focus on the service providers alone, then they're going to be deciding what we can do with the network. But the point of, or the great thing about how the internet is neutral today is that we're all connected, or we could all connect to each other. We don't really have to use these service providers. We tend to. This is somehow a human nature to sort of go towards centralization and monopolization, but the internet is a tool that would allow us to try more variants or other kinds of structures, and we need to be aware of that and the importance of net neutrality. If we don't talk a bit about the network, we might lose it. So, how did it all get started? In 1970. Then ARPA, they started the ARPANET. So ARPA back then is now DARPA. That's the Defense Advanced Research Projects Agency. They developed technology for the US military, and they did back then as well. So the ARPANET was, as the quote says from this very, very old document, that the objective is to get all their suppliers connected into a network together and being able to exchange information so that they can, I guess, make progress more quickly, more efficiently. Right? Now it's something else. I think that's good. So let's look at what happens between the browser and a website. So we have a person using a laptop, and they have a browser, and they type in a web address, events, CCCDE, for example, to read the blog post, the latest blog post about Congress. So then the browser really does two different things, first of all, or to get to show this page. So first of all, it has to ask for the way to reach this website that we want to reach. Computers, they don't deal very well with names or text, at least not the network part of computers or systems. So there's this translation, somehow like a phone book, I'll get back to that in a bit, called DNS, which is used primarily, it has a few other uses as well, but it's used primarily to get from this name that we entered, events CCCDE, that we can also somehow easily remember, to the network address, the IP address of this website. So that's part one. And it says system DNS because the browser doesn't do all of this phone book lookup itself. It can rely on the operating system to take care of this, fortunately. So that's the parentheses, that's what the operating system is doing. It's using a few protocols, UDP, IP, and that becomes a network packet. We'll get back to those in just a little bit. So once the browser has the network address, the IP address of this website, it creates a connection. So it contacts the web server. And it uses this set of protocols. So it first uses IP to reach the IP address of the server, and then in particular it uses TCP for this connection type. We'll get back to those in a little bit as well, what their properties are. And on top of that, the browser then uses the HTTP protocol. We'll see an example of that in the very end. How or to request the web page that we wanted to see. And that's all happening on the laptop, in the browser, and part in the operating system that we're using, whatever that might be. Then there's, of course, this long chain, or sometimes not so long, but usually several machines along the way, routers. We might have a wireless router at home, or in a coffee shop, or here at Congress. And beyond that, there are certainly some more routers along the way from or between my laptop, and the destination that I want to contact. So all of these routers, they receive some packet. They look at the addresses where it's going in particular, and then sends it along its way. So they're just forwarding packets all day long. Finally, at the destination on the web server, there are also two parts. So first of all, the request that was sent by the browser is received. It goes through these different layers, these different protocols, and the website server software, it looks at the request and it sees, okay, somebody wanted the first blog post, then I'll send that right back the same way that I received the request. And that's part two, so returning the response to this request. And it goes all the way through the routers, the same path, but in the reverse direction to the laptop. So let's look at all these different building blocks, right? So let's start with the smallest one, the network packet. I talked about packets going back and forth. So the packet, or a packet, is sort of the atom on the network. It's the smallest useful unit that is sent or processed by the network. I think a good way to explain packets is with regular postcards that we can send with mail, because their size, their maximum allowed size, is pretty much standardized. You can't send a postcard which is 1 meter, right? And it's the same with the network packets. You can't send arbitrarily large network packets. One pretty common maximum size is 1,500 bytes, or roughly characters. So just to give an idea of how fairly small the packets are actually, and even that might I don't know, do 1,500 characters fit on a postcard? No, I guess not. I think that's too much. So maybe the packets are a little bit larger than postcards, but still the analogy is pretty good, because you send them out and there's very little, there's a little bit of structure, like there's a stamp perhaps and a recipient address, but that's pretty much it. So what you write on the postcard on the other side is really up to you, and it's the same with the packets. They can contain anything, but if you write in a language that the receiver doesn't know, then they're going to receive the packet and then actually just drop it because they don't know what you're trying to tell them. So packets, they are sent and received through network interfaces. This is an Ethernet cable, LAN port, or a Wi-Fi antenna, or maybe a 3G modem if you're on the go, out and about. And your cell phone does this, of course, as well, right? The cell phone has Wi-Fi if you're in a coffee shop maybe, or it has 3G if you're in the subway or on the tram. And one interesting thing, or where the comparison to the postcards doesn't really fit anymore, is that network interfaces, they can easily pass millions of packets in a single second. So it can be quite a lot of information going through, especially if you have a good internet connection, like here at Congress. So then the next step, or sort of if we start looking at, okay, what can we put on the information side of the postcard, right, where we can put any message we want. For this talk, I'm only going to focus on IP version 4. I know it's old and legacy, and we really shouldn't be using it still, but it is it's dominant so far. It won't be forever, but so far it's quite common, and I think it's something that most of us have at least seen when setting up the Wi-Fi or the new internet connection, right? This IP address that I put up on the slide is maybe the most common IP address there is, right, for the new wireless router. These IP addresses, they consist of the 4 numbers, and the 4 numbers, they range from 0 to 255, and then there's 4 of them, and with dots in between is just how we write them. This is an efficient way for machines to identify themselves, but the reason IP version 4 isn't so great anymore is that it's quite a small number of addresses. So it turns out that the internet is pretty popular, and worldwide the addresses have run out or are running out. There aren't enough addresses for all the devices that are actually participating or somehow connected to the internet. IPv6 will solve this. Let's see. Maybe we'll live to experience that. So what is a network then? There are different kinds of networks. I've written physical networks and logical or abstract networks. Physical network is cabling, right? If you have some kind of connection from your internet service provider, it goes to your wireless router, and you have or if you have a LAN set up, like in the Hack Center, with a switch and lots of cabling, cables to one cable to each computer, that's a physical network, and that's a tangible thing, right? That's something we can touch and we can modify with our hands and so on. But then there are also, and that's certainly one network type, and another equally valid network type is the logical network, or as I also call it, the abstract network, which is defined only by the addresses used by some set of computers that are communicating together. So here's an example of an IP network that might be used with the wireless router that has the IP address up on top, right? And there's sort of a pattern, right? The first 3 digits are the same, and that's the address, the network address, and the very last part is 0. with the /24, meaning the 24 first bits of the 32. So now it's technical maths and binary, and sorry. But essentially the 24 means the first three numbers are always the same. And within this logical network, so within this group of computers or systems that can communicate with each other, only the very last digit will change. And as long as this is the case, we don't need a router yet. We can, all these computers or all these systems, they can communicate directly with each other on the local network or on a Wi-Fi or whatever. And the /24 and with the 255, 255, 2550, that's just two different ways to express exactly the same thing. So where do these IP addresses come from, and who has them, and so on? So if we get a wireless router, then we have some IP addresses, but me and my friend, we both have the same perhaps IP addresses because we have a wireless router from the same supplier, right? And this is a little bit of a special case. Those aren't internet IP addresses. They're used only very locally, so only in one home network, only in one company network, perhaps. The public IP addresses are the ones that are on the outside of this wireless router that I got, and the wireless router typically only has one. Some internet providers give you a few, but it's very easy to have a lot more devices in your home or in your office than public IP addresses that you get from your internet provider. So the IP addresses, they're assigned to the internet providers, and or the other way around. Internet providers, they apply for some range of some number of IP addresses, and here in Europe there's an organization called RIPE in charge of allocating a block of IP addresses to the internet companies that are actively connecting to other internet companies, and maybe are also your internet providers and mine. So and RIPE, they of course have colleagues in different parts of the world. So I think there are 4 or 5, maybe even 6 of the RIPE organizations, the regional network centers. They assign IP address blocks to the internet companies, and by internet company I don't only mean internet providers that we use at home and at work, but also really any larger company that has a service available on the internet. So all the streaming sites that you can imagine, all the several large just websites that are used every day will also have their own IP address range and will be active in finding different ways to connect to the internet providers so that the end users can have as good an experience as possible when they're visiting or using their services. So I talked about the internet companies. They are trying to find good ways to connect to each other, or to make it possible for users with one internet company to reach either users at another internet company, or some service provided by some internet company. And that's the routing that's going on both in the wireless router at home, but just as well and even more so in all these routers on the internet that are handing packets back and forth. So starting with the wireless home router, it typically has one local network. At least it might have more. So I had a home router that had both the regular Wi-Fi network, and I was also able to configure a guest network or a guest password. So that's actually it's Wi-Fi, so it's not really so intuitive, but those are two separate physical networks, because if you're connected to one, you can't communicate directly with the other network. without a router. Now there's some chance that the wireless router will do this, will enable this communication, but it's not for sure, and it's not certain. And in fact, it's more likely that it won't work because this guest access, you're supposed to be able to give that to somebody who's just visiting, and maybe you don't want them to access your printer or your storage cabinet or whatever, right? So it's quite likely that this guest network doesn't get access to the main network. So two different networks, even though it's the same radio waves or the same air that's carrying the radio waves, but the key property with a wireless or a home router is that it almost always only has a single internet connection. So it has a single connection to some internet provider or in the direction of the internet. Typically, that's the telco, but in some cases, there's even, especially in the US, there's the situation where the telco or the internet provider is also a content service provider, and that's a pretty bad situation, in particular if you have no options, no choice. So we have the home router with a single connection towards the internet, to the internet provider. Let's compare that with the internet routers that are further out on the internet and operated by the many different internet companies. They will similarly have one or more local networks that belong to them, the same way that the wireless network belongs to the home router. A wireless company, or an internet company or an internet organization, let's say like the CCC as well, has some equipment, some servers. With the events CCCDE server, for example, is part of the CCC slice of the internet, and the router that's responsible for all of CCC's networks is responsible for also this IP segment where the web server is. Now the big difference here is that those internet routers, or the routers that are further out on the internet than our home routers, they typically connect to at least two, but usually many more other internet routers. Exactly how is different in every location. There are some norms and some common topologies, but this is so the connections that exist are determined by peering agreements between the internet companies and their internet organizations. They can of course have agreements with whoever, so it's not so easy to tell beforehand what a particular organization, how a particular organization will do peering. This is an interesting topic. There are some more talks on this as well that I'm referring to later. At least one model is to have a site, some data center somewhere where an internet exchange is running. So this is an organization whose sole purpose is to enable many different internet companies or internet organizations to somehow make their way there, put some cables to this data center, and all connect together and be able to exchange traffic between each other efficiently and maybe even at no cost. So that's an interesting topic, because there are so many different business models for this peering, for the peering agreements. So the internet exchange is one model. There's a handful of them in Germany, and yeah, that's about the scale of it. Private peering is of course possible too, where organizations just have a direct connection between each other. And okay, so these connections, they are then established somehow, and how do the routers know where to send what? And that's a good question. This is managed by routing protocols. BGP is one such application, or a bird is one application, and BGP is the protocol. So there's some rules. You can configure what to prefer, what route to prefer, but you can also just say I don't really care so much and just use whatever is available. And of course, this depends on how much you have to pay for traffic that you send which way. If you have a really good peering agreement with another internet organization, and you're able to send a lot of traffic their way, then without having to pay very much extra or maybe anything at all, then of course you're going to try to send as much traffic as possible that way. All right, so now we're getting we've looked at IP addresses, and IP addresses, we know some systems on the internet or connected to the internet. All systems connected to the internet, they have some IP address, and if we know the IP address, we can try to reach that system. Yeah, that's a bit unfortunate. So the first bullet point is UDP. It's now we're talking about, okay, so on the postcard when we're writing stuff there, we put the IP address because we know what system we want to reach, but we want to send it some kind of message as well. There are a few different ways to structure messages, and these are the most common ones, or the ones that make up almost all of the traffic on the internet. So the first one is UDP. It's quite like postcards. So it's just a single message. There's no context. There's no connection between two different messages, and there's also no guarantees about how this message will, or this packet will perform on the network. So if you send out a UDP packet, it might arrive or it might not, and you'll never know. And that can seem a bit useless, but actually it's quite good in many cases. For example, if you're doing real-time audio or video streaming, UDP is a good choice because it's real-time information. So if something is missing, maybe there will be a glitch in the audio, or there will be some glitch in the video, but that it's not so important to wait and delay the image to fix that glitch. It's better to get the next image and just replace the image. So just keep on going, and for that UDP is a really good fit. It's just send it along, and if it arrives, it arrives. Most of the time it does arrive. Most of the time it works fine. So sometimes a good choice. The next point there is TCP. So maybe you've heard the term TCP/IP, and TCP/IP is exactly so specifically it's the combination of this TCP that I'll get into in a second with the IP addressing. Both TCP and UDP, they have the concept of a port, so that's a second address. You could compare that with let's say the IP address is the street name, and the port is the number, the house number on that particular street. So it's a bit more precise. You know it's that system, but that system might have might offer many services, and you want one specific one. So for each of the common services that we use, email and web and Jabber and whatever, there are typical port numbers that are allocated, and always the same, so that I don't have to guess or look up what it is. So with TCP, what are the properties of that? That's more like a stream of letters that you have to go to the post office and acknowledge that you've received. So the recipient of a TCP packet or a network packet with IP and TCP inside of it will always confirm reception to the sender. So this allows this concept of a connection that I mentioned, where both sides talking to each other are synchronized and know where the other party is in this communication or in this connection, what data has been received and what has not yet been received. So the packets, TCP packets, can of course also get lost, right? There's no guarantee with any network that it will always function correctly. You can just pull the cable and it will not be possible to send any packets. So TCP will recognize that, oh, so I sent some packets out, but they haven't been confirmed, they haven't been acknowledged. Okay, I'll try again. I'll send again a few times, and it's usually adjustable how long TCP will be retrying to communicate, and finally it will give up and say, yeah, sorry, it seems that this connection is broken. It's not possible to communicate anymore over this path. But if you're quick and you plug the cable back in, then maybe everything will heal, or the connection will just continue functioning just as if there was never an interruption, because the network software is keeping track of what has been sent, what has been received, and can recover from this loss of communication. And the third one on the bottom is SCTP. This is not quite so widespread, but it's still a very powerful mix. It's a lot younger than the other two. So UDP and TCP, they're from the I'd like to say 70s and 80s. Yeah. So quite old, whereas SCTP is, I think the standard was final in, or the first version of the standard came in 2000. So it's quite a lot younger, this protocol, but it's a powerful combination of properties from from the older ones. So you can have, whereas TCP, you just have a constant stream of text, essentially, or image, or whatever content you're transferring. With UDP, you had this message that's on the postcard, like it's one postcard that you're sending. That's the fixed message. TCP doesn't have that concept. It's just information all the time until the connection closes. SCTP, you can have a connection concept where both sides are aware of the communication status or the position in the communication, but you will be able to you will still be able to send messages like on the postcards or like the postcards. So you have a fixed size piece of information that you want to transfer, and you can send that as a unit. Whereas if you're only using TCP, like we do on the web all the time, you have to build a lot of stuff around or on top of TCP in order to achieve the same thing. So if I want to transfer an image, or when my browser wants to download an image, there's quite a lot of extra work that has to go into making that possible with the regular TCP protocol that is being used for now. So advantage, SCTP certainly. It also has the retry, the reliable delivery, if you want to, and you can also use multi-homing. So that's not so common yet. As I said, typically the wireless home routers, they only have a single internet connection, but that might change. We might in the future see several different kinds of internet connections that we're using. And SCTP would be able to take advantage of that quite easily, whereas the other ones cannot. So SCTP can send the same information over several different connections, and whatever comes first, arrives first at the destination is accepted. This is of course a bit wasteful, but in some cases maybe it's not a problem. So that's an exciting, I think, exciting new feature. Let's see what the future brings. It seems that TCP is going away slowly but surely. Let's see what happens. But some companies, they're providing systems where they want to control much more of how the software is using the network, how the software is communicating on the network. And the way that these systems are built, cell phones typically, or smartphones, it's not so easy to do that with either TCP or SCTP, but it's quite easy to do it if they're using UDP. So I think that's a big motivator for them to try to move away from TCP and use UDP even more. Let's see. Oh, sorry. So then we'll get into some applications. Now we've written on the postcard, we've written addresses, IP addresses, the system that we want to communicate with, and we've chosen either UDP or TCP, depending on what is most suitable. Actually, it depends typically on the application. So some applications require one or the other, and a few applications can do either or. The first thing I'd like to mention here is DNS. I call it the phone book, the internet phone book. So, but there's one big difference. A phone book is something we get from one publisher, right? The phone company typically, and or the POC here at Congress, and they've just collected, or they know all the phone numbers, and they send us the list, right, with the names. DNS is different in that everybody who has a name in the DNS, in the domain name system, so anybody can register a domain name, and anybody who does that can publish some information there. You can decide what you publish. Actually, you can decide if you publish. So let's say you have 1,000 IP addresses. You can decide if you want to publish names for all of those 1,000, or if you just maybe publish a few of them that are going to be interesting for other people to use, and 90% of them are just internal systems. So everybody gets to choose what they publish, and everybody can publish, also can run the infrastructure storing this information on their own. So it's not that you have to send this in somewhere necessarily and they publish it for you. You can actually do that on your own. So it's decentralized, very good. Still, it's a super old protocol, also from those early days of the internet, and nobody was thinking about security, and nobody had done a lot of attacks on on these protocols, whether it be reliability attacks or just forgery attacks and so on. That wasn't a concern, because this was, remember, designed for companies working for the government, right? So everybody was interested in collaborating, and there were no bad actors. The internet now is again quite different. So some of these old, well, most of these old protocols actually aren't so great anymore. Basic functionality of DNS or the phone book is to publish IP addresses, but you can publish other things as well. If you're interested in DNS, there's a good talk about that later on. I'll mention in a bit. So the next application I want to talk about is SMTP, or the next application protocol, Simple Mail Transfer Protocol. This is what is used to deliver every single email in the world all the time, all day long. Now, one thing that's a bit interesting, or quite interesting, but also problematic, I'd say, about email and not SMTP per se, perhaps, but the scope of SMTP is that SMTP is used only to send email. So SMTP doesn't have anything to do with receiving email. This means that there's a separate mechanism for receiving email, and the way these two different protocols or mechanisms work end up putting the cost of email with the person receiving mail. So I have to pay in order to, either with information or with money, to get an email address where I have some gigabytes of storage. Whereas people sending email, they don't have to pay anything. They just need an internet access, and then they can send all the email they want all day long to every single possible email address in the world, and that's why we have a spam problem on the internet. So this is, it's a bug. Let's see if this can get fixed. Email is so tightly integrated into our everyday lives that I'm not sure. But let's see, that would be great. So on the last one, the last application protocol I want to mention is the HTTP, hypertext transfer protocol. That's used for web, right? You recognize it from the web browser. URLs. Web pages used to be just hypertext, so text with some links, and then that's all they could do in the very beginning. And I'd like to show an example of SMTP. Actually, I have to do something about this because it's not so easy to read. Let's see. Right. Yeah. I should have done that already. Sorry about that. So this is an example of an email delivery. This is all it takes to send an email on the internet, and the left and the right on the edge there is so the arrow pointing that way, right, left, is received from the email server, so from the SMTP server, and the arrow pointing this way is what we send to the email server when we want to send an email. So if we connect to an email server, for example mine, it will say, send us some text. We're using, by the way, TCP, and we're using port 25 for SMTP. So we get a stream of text going back and forth. The server tells us 220 and its name. That's some kind of welcome code. We say hello. My name is laptop because I'm doing this for my laptop. The mail server says, okay, good to meet you. And then we say, I want to send an email where the sender address is test@stuge.se. And if you're paying attention here, the sender of the email gets to say what the sender address is. So this is why it's super easy for anyone to forge email from any sender address. It's part of the message, or part of the message. Server accepts the sender, even though the sender might not even exist. I tell it, recipient, this is for me, mail for me. Server says okay. Then I say, here's the data for this email, and the server says, go on, start sending me the contents. And then I send an email where the sender is trollolololol and just some fake sender address, whatever subject, and some text. And in the end, I finish with a dot to say, okay, end of message. End of mail. The server says okay, and then I say to the server, I want to quit now. I don't want to talk to you anymore. The server says closing, goodbye. And this is email on the network. Last example. A web page access over HTTP. So this is even simpler. I've simplified this even a little bit more. If you try this yourself, please do. So HTTP is also TCP and port 80. I tried talking to the events CCC.de web server, and I told it same thing here. Arrows pointing this way is what we send when we contact the server. So connection opens. I send get / and HTTP 1.0 because I want to get the main page, and I'm saying I'm speaking HTTP version 1.0. And then I tell it, okay, I want to access this start page on the host name events CCC.de. Then I send it an empty line. That's to say, okay, this is my request. And then there comes the response, comes back, the arrows going in the other direction, where the web server says, actually, so what you're asking for, it's not available here where you're asking for it. You have to go somewhere else. It's a redirect. That's the 301 is the code for HTTP code for redirect. And this contents that you're asking for, this page, it's been moved permanently. The new location is HTTPS events CCC.de. So I was using an IP and TCP connection with no encryption, and that's why I can just type in the get and the host line. But the web server tells me, yeah, sorry, I don't want to talk to you without encryption. So you have to go to this HTTPS address instead. Thank you, event CCC.de. I like encryption, that's good. And thank you also to all the angels that make Congress possible, because without them and without you who are here, who are angels, there wouldn't be any Congress. And also I want to say a huge thank you to you in the audience for being curious and wanting to learn something new.
Thank you very much, Peter. Now we have some time left for Q&A, so if you have questions, please do line up at the microphones that you find here, if you want to ask anything. Do we have a question from the internet? No, the internet is out of questions. Do I see anybody standing at any microphone? Please make yourself known if I overlook you. Any questions? Oh. At microphone 5, please do ask your question.
Yeah, you mentioned that you think SMTP has a kind of bug in the sense that you can just send an email and the responsibility is on the side of the receiver. So if you call it a bug, it seems you have an easy solution.
I'm sorry, but no, I don't. So there was, I mean, I wish that would be great. It's not so easy to fix because it is a property of SMTP, right? And of the email system that we're using. So there was a proposal a long time ago by somebody much smarter than me called Internet Mail 2000, where actually the whole thing is switched around so that the sender has to store the message and the receiver can go and pick it up. So there the cost is placed on the sender, and I think that would go a long way to solving the spam problem, but it's not compatible with the email software that we have today. So I don't it's not clear to me how we would be able to migrate in a good way, unfortunately.
Thank you. Do we have any other questions? That does not seem to be the case, so please give another warm round of applause to Peter Stuge. Thank you very much for the talk.
Right. Thank you.